Evan, 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 the calc teacher! Yay! Hi, I'm Evan, and I'm a calc teacher. You should already know me by now. Would you like to go on a calculus adventure with me? Great! Let me introduce you to my friend, my fiance's Boots. Boots and I like to go on adventures all the time, and we'll go on an adventure today. To get started, I need to find my backpack. Do you see my backpack? Backpack, backpack. Do you see my backpack? That's right. It's the pack on my back. Let's see what's inside the backpack. Look, it's our calculus book. Do you want to learn some more calculus? Great. What chapter should we be on? Five. That's right. Oh, wait. 6. That's right. Chapter 6. We're going to the land of antiderivatives. And with that, let's look at the notepad. Antiderivatives. Okay, so the first thing we need to know about antiderivatives is what are they? Well, let's dissect the word anti and derivative. Hopefully all of you can figure out exactly what anti means here. It means the opposite. And derivative is exactly what you would expect it to be. It's the opposite of a derivative. Basically, in some sense, what this means is that we're going from f prime of x to f of x. And we can also use the notation spelled that wrong. F of x goes to capital F of x. We will use both of these notations. And we have a special symbol for the antiderivative. Which is looks like an elongated S. Also called esh if you're talking about the symbol itself, and we call it the integral sign. We also need differentials. So that really what we write down is the integral sign f prime of x dx equals f of x. So this dx, d of some variable, needs to be the same variable that's in the function. So that's how we talk about antiderivatives. We're going to find out that the S here, this elongated S, really stands for a sum, but that's going to be a few days out. So let's talk about some very stereotypical examples of antiderivatives. Say of common antiderivatives. Okay, so common antiderivatives, we're going to have something like the antiderivative of 0 dx. So what do you guys think the antiderivative of 0 might be? Well, what do we have to do? We have to think about d dx of something equals 0. What should this be? And that's a really good question. What should it be to be 0? Well, a lot of you are probably saying 0. D dx of 0 is indeed 0. But can any of you come up with another function that I could put in to get 0? Is there another function that becomes 0? Yes, I'm relatively certain some of you have come up with this. D dx, let's try 8. I think all of you would agree that 8 also becomes 0. D dx of -5 becomes 0. D dx, and now I'm going to write this in the way that we're going to see it very often. D dx of c, any constant, becomes 0. And you guys are all like, yeah, we've been doing this for 3 months now. Well, d dx of any constant becomes 0. If that's true, then this antiderivative of 0 has to be any constant. So far, there's not enough information to tell us what this constant is. So when we don't have enough information, we just leave it as plus c. So we leave it as c. So that's a good example of one common antiderivative. And what about other common antiderivatives? Well, let's just do one step up. Let's take the antiderivative of 7 dx. Well, to still be an antiderivative, what do we require? We look for functions such that f prime of x is 7. So it's a good example of a function that has that property. And hopefully some of you can come up with this. F of x equals 7x has this property. I'll say since d dx of 7x equals 7. But then I ask again, are there other functions? With such a property? And some of you might say no, others of you might say yes. And the ones of you who say yes, I would say, give me whatever you think. And you would tell me d dx of 7x plus c, where once again c is any constant. Since the derivative distributes onto the 7x and the c, we really get 7 plus 0, which is, of course, 7 here. So really, the integral of 7 dx is going to be 7x plus c. And once again, this is any constant. What does this say? This says for all antiderivatives, we have the integral of f prime of x dx is not just f of x dx, but it's really f of x plus c for any constant. And so I'm going to circle this now because this is a pretty big deal. And then I'm going to give you some of the generic rules that we're going to follow when we're taking antiderivatives. So here's the properties. Let's say properties. Properties of antiderivatives. Well, they're just the opposite of derivatives, so we have the very basic integral of f of x plus g of x dx. Put those in brackets. This is the integral of f of x dx plus the integral of g of x dx. And we get the same thing with a minus sign. The integral of f of x minus g of x dx equals the integral of f of x dx minus the integral of g of x dx. And finally, just like with derivatives, if I have a constant multiplier, we can think about that as a constant or as a number, then that can pull outside of the integral. And these are really all the same properties we saw with derivatives, right? The derivative distributed over plus signs, it distributed over minus signs, and constant multipliers, that's the special part, is that the constants have to be multiplying the function. Constant multipliers get pulled out front. So let's come up with this power rule. Power rule for antiderivatives. And we're going to get used to this other word, integral. They really are synonymous. The power rules for antiderivatives or integrals. We want to be able to handle expressions of the form x to the n dx. So we want that equal to a function, and a good guess would be, well, derivatives we should all remember our power rule by now. The exponent jumps out front, and we subtract the top number by 1. So the derivative is taking the exponent out front, and it's making the top number by decreasing it by 1. So let's try. Let's try the integral, maybe, of x to the n dx. Let's do x to the n plus 1. That seems like a good idea. But then instead of bringing the n, right, in this case there was this n here. And, what do we do with an n, something like that? Well, let's see. So in the derivative case, it was multiplying out front, and it was the exponent. So the exponent multiplied out front. Let's try dividing by the exponent and see what we get. And yeah, there should maybe be a plus c on the end, but let's not worry about that right now. So let's try dividing by n. So we ask the question, does this work? Well, we can always check our antiderivatives by taking a derivative. So what I mean by that is if I take a derivative of this x to the n plus 1 over n, hopefully I recover x to the n. So let's try that. dx x to the n plus 1 divided by n. And that n is really behaving like a constant multiplier. So I'm going to call this 1 divided by n times d dx of x to the n plus 1. And let's see what we get. Okay, so the exponent here is n plus 1. So this exponent is going to come out front, and we're going to get 1 over n times n plus 1 times x to the n plus 1 minus 1. And if I simplify that, I get n plus 1 over n x to the n. And what I wanted to get here was x to the n, not x to the n with this term out front. This term out front is bad. This is not what we wanted, right? Because this is not equal to x to the n. Our whole idea was up here that x to the n is exactly what we wanted. And that's not what we're getting. So what could I do to change this piece here, this n plus 1 over n out front? How could I change that to just be 1? Well, it would have been 1. It would have worked if the denominator was n plus 1 instead. So let's say, so this is wrong. That's wrong up there. But with the denominator of n plus 1, I feel like we might be right. So now we're going to try that the integral of x to the n dx equals x to the n plus 1 divided by n plus 1. And all of you are probably already seeing how this is going to work, because the integral of, we're going to take derivatives of both sides actually. So let's take a derivative over here. Let's take a derivative of x to the n plus 1 divided by n plus 1. And just as before, this piece comes out front. And then when we take a derivative, we get n plus 1 divided by n plus 1. X to the n plus 1 minus 1. And lo and behold, those cancel and we get x to the n. So that's exactly what we wanted. And that tells us our power rule. The power rule for antiderivatives, also known as integrals, is given by the integral of x to the n dx equals x to the n plus 1 divided by n plus 1. And as always, plus c is incredibly important. I didn't do the plus c in our derivation there just because it's going to turn into 0 anyway both times, but the plus c is always very important. So this is 90% of what you're going to use. Just like when we were doing derivatives and we use the power rule for derivatives 90% of the time, this is going to be what we use almost all the time with antiderivatives. So let's try to apply this. So we'll apply it in the case of, let's do x squared plus x cubed dx. X squared plus x cubed dx. I'm going to jump up really quick to here, the properties of antiderivatives, and we have this plus property, right? The antiderivative will distribute over addition. And so here when we're working with x squared and x cubed, it's just like derivatives. We work piece by piece. So working piece by piece on x squared and then later x cubed, we just want to follow our power rule. So what does the power rule really say? It says take the power, take the exponent. This is n in this case, right? The exponent n, we're going to add 1 to it, and then we are going to divide by that new number. So how do I want to think about this? So I'm going to take x to the 2 plus 1, and what's going on? Whatever's in the exponent when I'm finished, 2 plus 1, I'm dividing by that as well. And the same thing happens with x cubed. And so if I want to simplify this, it simplifies pretty easily to x cubed over 3 plus x to the 4th over 4. And now this is the point at which all of the math memes are made. Everybody always talks about doing an integral perfectly and then getting a 0 on the problem because they forgot plus c. So just don't forget about plus c. I'll do my best not to take points off for you guys, but if it becomes a huge problem, I'm going to. Just don't forget about plus c. It's always going to be there, so you might as well always write it there. Let's try another example. This is more similar to something you might encounter on the homework. Make your lives tough a little bit. Let's do the integral of the square root of 10 plus 3 times the square root of x dx. So what's going on here? Well, I can certainly split it up over the plus sign, so I might as well start out with that. And that square root of 10, this might seem like a shocker to you, but I'm sure you can trust me once I say it, it's just a number. The square root of 10 is just a number. So just like way back, and I'm going to jump all the way back now. Right here, 7. 7 was a number. Right here. So 7 was a number there. And the integral of just a number is that number times x plus c. So let's go back here. The integral of a number, in this case the square root of 10, the integral of a number is that number times x. So that's what we're going to do here. Square root of 10 is just a number, so the integral of a number is that number times x, and there's a plus c, but I'm just going to add it at the end. We have to handle this other piece. This other piece seems a lot trickier. 3 times the square root of x dx. 3 times the square root of x dx. Well, I'm sure you're all thinking back to when you were working with derivatives, what the square root derivative was phrased as, and you'll remember that the square root derivative was really phrased as x to the 1/2 power. So instead of the square root x here, I'm going to write it as x to the 1/2 power, just like we did when we did power rule for derivatives. Square roots are 1/2, and then we can almost apply our lovely power rule here. But we have one extra special step, and that's that we look up to our properties here, and we see that if there's a constant number that's multiplying our function, then it can pull outside of the integral. So the constant number multiplying pulls out. So if the constant number multiplying pulls out, what do we actually end up with? We end up square root of 10x plus 3 times the integral of x to the 1/2 dx. And now we can really use our power rule on this piece, this x to the 1/2 dx. So the power rule on x to the 1/2 dx maybe is not explicitly clear right away how you would use that, but just try to pretend it's like our derivatives, but we're working in the opposite direction. You take the exponent here is 1/2, you add 1 to the exponent, and then you divide by that new thing. So let's take it, x to the 1/2 plus 1, and we divide by the new exponent, 1/2 plus 1. And 1/2 plus 1 maybe doesn't seem like something you want to calculate, but it's 3/2. So I end up with the square root of 10x here, plus, really I have 3 divided by 3/2, and if you don't believe me what that is, it's how many 1.5s fit into 3. Well, 2 of them do. So 2 1.5s fit into 3, and I have x to the power 3/2. Don't forget your plus c. Pretty good. I'm going to go over one more actual rule for derivatives now. The rule that I'm going to go over for today's lecture is the antiderivative of an exponential. antiderivative of e to the x. And with the way last week went, although only 17 of you were there on Friday, with the way it went, hopefully you can believe me that if d dx of e to the x equals e to the x, then the antiderivative of e to the x, who has an idea of what it should be? Discuss it with your friends. Oh, I'm sorry, are you all alone? Sorry, never mind then. It's e to the x plus c. So that's not too hard, right? The antiderivative of e to the x should be the same just because the derivative was the same. All right, so let's just do one more example, and this will prepare you for your homework, and then we can be done for today. So one last example to prepare you for your homework. We're going to do the integral. Now I'm going to be tricky, really tricky. 1 divided by the square root of x to the 5th power plus square root of 2 e to the x dx. As always, this integral happens in 2 parts. So we're going to split it into those 2 parts. And just as before, numbers can pull right through. So hopefully that piece made sense. But the tricky thing here is 1 divided by the square root of x to the 5th power. Square root of x to the 5th power, how do we want to think about that? Well, as always, we want to think about square roots as x to the 1/2 but that doesn't solve our problem completely. Here, for e to the x, I just kept it as e to the x because, look, there's our rule. Pretty easy. But we have to work a little harder on this first piece one more time. So let's see if we remember how our exponents work. If I have 2 exponents, I have an exponent of an exponent, well, kind of parentheses, and then another exponent. Those are going to multiply. This is going to turn into 1 divided by x to the 5/2 dx. And I have a power that's in a denominator. So we really can't stress this enough still, that powers in denominators are negative powers in the numerator. So now that we're looking at x to the negative 5/2, this makes a lot more sense as to how I can use my power rule. I just take x to the negative 5/2, I add 1 to it, and I divide by negative 5/2 plus 1. And as always with exams and whatnot, I would have no problem with you turning in a solution of this form. But I'm going to simplify it a little bit more. Negative 5/2 plus 1 is negative 3/2. So this really becomes x to the negative 3/2. And then in the denominator, a negative 3/2 in the denominator is the same as negative 2/3 in the numerator. And then I'm just left with the square root of 2 e to the x. As always, don't forget, plus c. So that's the last one I'm going to cover for you guys today. As always, email me and go ahead with the Ask Your Teacher questions if you have anything. I posted an announcement on Canvas that covers everything you probably need to know for this trying time that we're in. I hope it all made sense, and I guess I'll see you tomorrow unless you're watching all these at the same time. Thanks.